Thank you. I'm Professor Sharon Harding, and I'm just going to introduce Prapa and welcome you to this inaugural lecture for Professor Prapa Kanagaratnam. And he's absolutely terrifically well-deserved appointment, of course. In fact, he's been a professor for a little while now, because that's the way of these inaugural lectures, that they come a little bit later on. I'm going to be very brief. I know that Prapa will share his journey with us in more detail, but just to say that he started off in Birmingham and then came to St John's College, Cambridge, with a scholarship. He has then did his medical degree and came to Imperial in 1998 with a BHF fellowship. And of course, he was extremely welcome coming along with the fellowship. We always love people who come along with that, so we were very pleased to have him. And since then, he's been a terrific mentor for us, a link to us for us with the engineering department. Obviously, he's world famous for his ripple mapping, but he's also really at the cutting edge of the engineering world. We're going to hear, well, he could tell us about his robotic technology, his wearables, that's so now, the wearables, for the non-invasive imaging. So I'm really very much looking forward to this lecture. I think it's going to be very enjoyable for a geek, for the clinicians, for the geeky clinicians, for everybody. So join me in welcoming Prapa.
Thank you very much, Sean. Thank you for the kind introduction. And thank you all for taking an evening out to come and listen to some electrophysiology. So abnormal heartbeats are one of the commonest reasons why people might get referred to go and see a cardiologist. And what I'd like to talk about today is trying to explain how we decide which of those abnormal heartbeats can be treated, which don't need treatment, which can be dangerous, and hopefully you'll get an understanding of what cardiac electrophysiologists do. So we're here today in the Sir Alexander Fleming building, which commemorates one of the pinnacles of achievement at St Mary's Hospital, when penicillin was discovered in this building just up here. That was about 50 years ago. Just over 50 years ago, but there was an equally momentous discovery at St Mary's Hospital, which took place about 50 years earlier than that. And that was in a building just round the corner. And that was by a man called Augustus Waller, who performed the very first ECG at St Mary's Hospital in 1887. Now, unlike Sir Alexander Fleming, Augustus Waller isn't as well known, but his achievements are probably just as great. Now, Augustus Waller did something very special. He took his esteemed companion, Jimmy, and got him to paddle inside saline baths and was able to pick up the electrical signals that his heart was generating. And these electrical signals that his heart was generating, he managed to convert, using his toy train, into the world's first ECG. So this ECG you'll recognize straight away. And what it was able to show for the first time was that electrical beats in living beings was causing the heart to pump and work. And obviously this is now used throughout the world. Whenever a patient goes to see a heart specialist, they will have an ECG done thanks to Augustus Waller. Now, our story starts a little bit later than this. So we're going to jump now 100 years. And another important occasion at St Mary's Hospital is a royal birth. And royal births are always very important because they often signify a new change, a new start. And this time, the new start was a new generation of cardiologists. And Rodney Fowle was one of the first people to introduce coronary angioplasty to St Mary's Hospital, and shortly after he was joined by Wyn Davis, who brought cardiac electrophysiology to St Mary's Hospital. Now, after the time of Augustus Waller, the ECG was just used for diagnostic purposes. And what Dr. Wynne Davis was able to do was use those electrical signals to actually give treatment for rhythm disturbances. So I'd like to spend a little bit of time explaining to you what was done at that time. So this is a normal heartbeat, and the electrical impulse starts up here in the sinus node, and it spreads out over the atria. And as it spreads over the atria, it triggers a contraction of the atria to push blood into the ventricle. The electrical signal then travels, after a brief moment in the AV node, down the ventricles and causes the ventricles to contract and push blood around the rest of the body. And then underneath here is the ECG, which measures those electrical signals just in the same way that Augustus Waller did. Now, in cardiac electrophysiology, we study those signals in a bit more depth. And what we can do is put catheters from the veins in the leg up to the heart, and we can record the electrical signals directly from the heart. So these catheters here have got little metal electrodes, and this one is sitting in the right atrium, which is up here. And when the electrical signal wave goes past that electrode, you'll see a little deflection in the signal up here. When the electrical beat reaches near the AV node, you'll see another electrical beat down here. And then eventually, as it reaches the ventricle, you see another beat down here. So this is the electrical wave spreading through the heart, causing it to contract. And this is what it should look like. But in people with abnormal heart rhythms, this pattern of activation changes. So one of the commonest abnormalities we see is a re-entrant circuit around the AV node. And when that happens, we can take a catheter and burn part of that circuit and cure the patient. And those patients are usually in their teens and 20s. And this was one of the first procedures that was done as an ablative therapy by catheters like this. And it was done by Wynne Davis, John Cam, and Anthony Nathan at Barts Hospital, and then shortly thereafter introduced here at St Mary's. Now, once we started treating these kinds of rhythm disturbances, we realized there were other rhythm disturbances that we'd like to treat. And this really triggered a sort of a growth in research in the area. And Professor Peters joined Wynne Davis to establish the cardiac research department at the electrophysiology department. And he took the science right from the cellular electrophysiology all the way through to 3D mapping, to try and understand the whole breadth of how electrical signals are generated in the heart and ultimately lead to both normal contraction and abnormal contraction. So I joined Nick as one of his first PhD students, and the project that I was working on for my PhD was on a condition called atrial fibrillation. And atrial fibrillation, instead of this smooth activation of electrical activity in the atria, you get these random reentrant wavelets that cause the heartbeat to become irregular. And this can cause patients to feel breathless, lethargic, and most importantly, it can cause some people to have strokes. So how are we going to investigate these electrical signals in atrial fibrillation to try and understand what was causing it and to try and understand how to treat it? Well, the technique that I was using was something called high-density epicardial mapping. And what this involved was taking an array with 128 electrodes on it that could be placed on the surface of the heart. So how do we place electrodes on the surface of the heart? Well, the only way we could do it is during open heart surgery. So when patients were having open heart surgery, we got permission from them to take some recordings of their heart just before the surgeon started performing the bypass operation. So we just recorded a few seconds of signal to be able to help us understand how these electrical waves were transmitted throughout the atria. So whenever we start a new technique or a new technology, we first use it just in normal rhythm, just to understand how it works and make sure it works properly. So we took initially patients who were just in normal rhythm, and we placed the electrode array on top of their atria, And each of these electrodes, just like the electrodes I showed before, would pick up a signal from the heart. So I'd go to each electrode, look at the signal, and mark a time at which it was activated. Go to the next one, and do the same again. And if you do that across the whole of the 128 electrodes, you could then identify the times of all of them, and all the electrodes that are activating at the same time are given the same color. So red is the earliest signal coming from near the sinus node, and you can see the electrical waves spreading around the atria. So this is the normal electrical activity of a patient in sinus rhythm. So then I went on to do the same again for people with atrial fibrillation. So now their atria are doing this odd thing where it's irregularly activating. And when I mapped this, sometimes the activation looked very uniform, almost like normal activation. Other times, it was completely irregular and disorganized. And each of these maps would take me about half a day to put together, checking each of the electrodes. And if I took 2 seconds of atrial fibrillation, I could draw out exactly what all the waves were doing, and this would be a few weeks of work trying to create one of these maps. So it was a step forward being able to map atrial fibrillation like this and see exactly where the wavefronts were traveling around the heart when the patient was in atrial fibrillation. But it was also quite a laborious process. And actually, over the period of time, although we developed the technique very well, we didn't make a huge amount of progress in trying to understand what the mechanism that was driving the fibrillation was. And that was probably partly explained by some very important discoveries that was taking place in Bordeaux in France. And this was literally at the same time as my PhD was taking place. The team in Bordeaux had noted that in the left atrium, so I was mapping the right atrium, but in the left atrium, they were picking up electrical signals that were coming from the pulmonary veins. And these signals were similar to what was going on in the sinus node, but going very fast and causing the patient to go into atrial fibrillation. So they appear to have solved the conundrum in terms of trying to find out where atrial fibrillation was coming from. And they also proposed a potential treatment for this by ablation, which was called pulmonary vein isolation. And pulmonary vein isolation involves putting a catheter into the pulmonary veins, here, from where the electrical activity was coming from, and burning point by point all the way around the vein so that those electrical signals couldn't come out of the pulmonary vein to cause the atrial fibrillation. This was a major discovery, and it was also a very common problem. So it drove a lot of technological advance and investment from industry. And one of the important advances that happened at this time was the development of a catheter system called CARTO. And what they were able to do is inside this catheter that we use for burning, they had sensors that could pick up low-level magnetic fields. And they could use three different fields that were placed, that were generated from underneath the patient to track the exact position of the ablation catheter. So what this meant was that we could use that catheter and the 3D information from that catheter to generate an image of what the heart looked like from the inside by moving the catheter around the atrium. So we'd move it to the edge, touch a spot, mark that it was the edge, move it to another area, touch a spot, mark that it was the edge. So gradually we could build up a picture of the atrium and use it to help us form these ablation lines around the pulmonary veins and hopefully stop atrial fibrillation. So these systems were designed primarily for therapeutic purposes. But actually, as someone who had used mapping to try and understand atrial fibrillation during my PhD, I also thought this was a very good way of trying to understand rhythm disturbances from a scientific perspective as well. So Pipin Jojo was my first PhD fellow, and he's now a senior electrophysiologist in National University Hospital, Singapore. And in true Pipin style, he's come over for the evening. And what Pipin did during his PhD was, just like I was mapping the right atria, he used those catheters to move around the right atrium and the left atrium to gradually build up a three-dimensional activation map of normal activation. So it's starting here in the right atrium, spreading around, going to left atrium, and going and reaching the end here. And unlike me, where I was only able to see just a part of the right atrium, Pipin could map not only the whole of the right atrium, but also the whole of the left atrium. And using this, he could also work out the conduction velocity of the electrical wavefronts. He could work out the refractoriness of the atria. And he used this to show that patients who had atrial fibrillation, not only was it being caused maybe by these triggers, but there were actual electrical abnormalities in their, the way their myocardium was behaving as well. And this will become relevant as we move on later on. We also used these 3D mapping systems in other types of tachycardias. And one type is ventricular tachycardia. And this is a life-threatening tachycardia. And if a patient has a heart attack or a myocardial infarction, they produce a scar. And on the scar, sometimes a little bit of tissue are left behind, which can cause a re-entrant circuit. And Mike Kerr-Wing, who is now a consultant electrophysiologist between Watford and Imperial, his PhD was trying to understand ventricular tachycardia using 3D mapping systems. So this is an example of a ventricular tachycardia case. So this is a map of the left ventricle, and this grey area here is the scar from the old heart attack. And you can see from within that scar this burst of red, which is where the ventricular tachycardia is coming out. And you see we've also ablated in that area to try and stop the ventricular tachycardia. Now this patient actually, about 2 years later, he died of unrelated problems, and he and his family were very keen that his heart should come back to us for research purposes. And so because we had his heart back, we were able to take samples from around here and identify where we'd done the lesions, but also found that within this scar, there was living tissue that we hadn't mapped. We hadn't identified the whole of the circuit that was causing this ventricular tachycardia. And part of the reason for this is because the signals that we use to create these isochronal maps can be quite difficult to annotate and to set the timing within these scarred areas. So we were beginning to build up this concern about isochronal mapping. So I struggled using it for mapping atrial fibrillation. Pipin didn't even try and map atrial fibrillation with it. And Michael could only map part of the circuit and couldn't map the scar. So I thought, well, maybe we should think again about how we map in 3D. And so Michael started working with one of my colleagues, Professor Darryl Francis. And Darryl Francis is not only an interventional cardiologist, he's also a mathematician and a computer expert. He's more recently famous for the Orbiter trial and infamous for his cardiologically speaking Twitter account. So you can follow him if you like. And Darryl and Michael together, they took the signals that they'd picked up from the CARTO system and started looking at it in 3D and trying to figure out whether there's some better way of looking at these signals. they went through several iterations, and eventually we decided that actually showing the electrogram as a bar moving from where it had been picked up was possibly the best way of trying to represent it in a different format. So we got to about this point, and I was very fortunate at this stage to be introduced to Nicholas Linton. And Nick Linton, at the time, was a junior cardiology trainee, and he'd also trained in engineering. And I was told that he was a whiz at computing and that might be able to help us with some of our problems. So I presented this problem to Nick, and I said, here we've got a map of sinus rhythm in the right atrium with activation going down here. And what I'd like to do, just as Daryl had shown, was to try and show each point as a bar moving up with the local voltage. And Nick, in his normal humble way, said, I'll try. And he came back a few weeks. Can you turn the sound off? Sorry. Can someone turn the sound off? Can you do it? Do I have to stop it to turn it? Thank you. Sorry about that. The reason that was noisy, by the way, is it was being recorded on a video camera by Michael. And so the talking and everything's in the background. This was from 2006, when we couldn't record videos on our phones. So this is what Nick came up with. So this is important because each of these bars were just moving according to the local voltage. And we hadn't annotated like we normally do during these mapped process, and it was only showing data from where we'd collected. But you can see straight away that without any annotation and without any pre-programming, the wavefront traveling down the right atrium. So because we thought that this had potential clinical applications, because it was able to do this process of isocardal mapping, but mapping without the user having to look at each electrogram, we thought that Biosense Webster, who manufactured the CARTO system, might be interested in this. So we spoke to them, and they said that actually they would be interested, but they initially put together a research version where we couldn't use it on patients, but we could take data from patients and have a look at it. So this is Shanaz Jamil Copley, who's a consultant electrophysiologist now in the Nottingham City Hospital. And her project was to try and understand how to use and interpret these ripple maps from patients that we'd been doing clinical studies for atrial tachycardias. So if I play this, so this was exactly like before. The bars are moving up and down according to the local electrogram voltage. There hasn't been any annotation by the operator, and all of you should be able to see straight away that you can see the electrical waves moving in different directions around the heart. So although it proved the principle that we could use ripple mapping to diagnose atrial tachycardias, in practice, we thought this was actually quite difficult to interpret. So we went back to Nick and we said, we need to change some of the ways that we're interpreting these signals. And one of the things that we realized we hadn't done was use the surface of the heart to actually to add information. And we also realized that you had to collect far more points around the heart to be able to see the wavefront. So we did this, and now you can see the wavefronts traveling around the heart. In the areas where there were no wavefronts and no activity or scar tissue, we changed the color, so it focused the eye on the areas that were important. And at this time, Nick and I often used to work quite late in the evening. And my 3-year-old daughter used to have this habit of waking up at that time. And one such evening, we were sitting there looking at this, and she came and sat down, and with her finger, started following the wavefronts around. And so I thought, I think we've got it. If a 3-year-old can diagnose atrial tachycardia, then anyone can. So we went back to Biosense Webster, and they agreed. They thought that this would help with clinical diagnosis. So this was the clinical version that we could now use in patients. So if I play this, you can see we had red where there was scar, there was no electrical activity, the white bars moving around the atria to show where there's activation. And Vishal Luther, who's one of our clinical EP fellows now, he was the PhD student who was tasked with trying to work out how to use ripple mapping in patients to make the diagnosis. So Vishal went through a process of adjusting all the settings and trying to understand what you needed to, how you needed to set the system to try and show what was happening. And hopefully, whilst you're watching the video going through, you also will have an idea of where these re-entrant circuits are traveling. So once he was happy that he had a good workflow, Vishal then started working with other teams in the UK and Portugal to teach ripple mapping to other physicians. And even very early on, it was clear that he was improving the diagnostic capability of electrophysiologists from 70% to over 90%, even in their first few cases. And part of the reason for this was because it was giving them far more information than they were normally used to. So this is an isochronal activation map with the latest version of the system. And you can see this red area here, which is where the activation seems to be coming from. And next to it, here, is the ripple map. And you can see on the ripple map, there's all these red areas, which is scar, which isn't obvious on the standard map. And when I play the ripple map, the electrophysiologist and the rest of you should be able to see that there's these little bits of electrical activity squeezing through that scar. And this is actually what we call localized re-entry with several areas of breakthrough. So where the standard map would just say there's electrical activation coming from here, the ripple map gives you far more information. In this other case of what we call roof-dependent tachycardia, we worked out the diagnosis, and according to the conventional map, you need to do an ablation all the way across here to stop the tachycardia. But if I play the ripple map now, same tachycardia, we see the scar comes very close to here at this point. So instead of having to do a whole line of ablation up here, we can break the circuit with just a single ablation there. So these were the reasons that we thought it would help physicians. And as we'd shown that it was beneficial in these early studies, Vishal then went on to do a multi-center randomized prospective study comparing ripple mapping against the standard approach. And in a couple of weeks' time, he will be presenting that data at the Asia Pacific HRS meeting in the late-breaking trial session. So unfortunately, I can't share that data with you today. But you may be wondering why we were having all these atrial tachycardias. And these atrial tachycardias were happening because we were doing a lot of AF ablation. And they're a iatrogenic consequence of having an AF ablation, because we were producing scar in the atria that was then acting as a nidus for these new arrhythmias. So I said at the beginning that certainly during my PhD, part of what my sort of progress in trying to understand the mechanism of fibrillation sort of came to a stop when pulmonary vein isolation started. So what's been happening with pulmonary vein isolation as a procedure? Well, between 1998 and 2003, there was a huge amount of progress. And back then, people were quoting what was called to be 70% success rate. But probably in the way that we define it now, it was probably closer to about 50% success rate with one procedure. So 15 years later, technology's advanced quite a lot. The atria that we used to create before with the 3D mapping systems look far more realistic now. The catheters that we use for ablation have got pressure sensors, and so we can deliver energy in a much more controlled fashion. But despite that, the success rate hasn't changed much. And even that is being optimistic. The latest prospective randomized study with a proper intention to treat analysis suggested that the success rates were closer to somewhere between 55 and 60% still. So why haven't we made progress in 15 years? Well, part of the reason is because all of this was based on this concept of pulmonary vein isolation. So this may just represent the plateau of where we can get to with pulmonary vein isolation. So if that's the case, then what we need to do is really try and think not so much about trying to make pulmonary vein isolation more and more complicated, but to simplify it, to make it cheaper, and get it out to as many patients as possible. And in trying to do this, we set up the Avatar AF study. And here we used what was called a cryoballoon, which is a freeze balloon, which can freeze the entire circumference of the vein in one go. And we tried to peel away every aspect of the procedure that we didn't think was contributing to its success. And we identified what we consider to be a streamlined Avatar ablation protocol. We set up a multi-center prospective randomized study comparing that against standard cryoablation and medical therapy. This was funded by the British Heart Foundation and Medtronic, and we worked in collaboration with the Imperial College Trials Unit, with Sasi Tyagaraja, the trial manager, and Daphne Babilis as the operational manager, and Nicholas Johnson and Emmanuel Falachetti, the statisticians. And the team managed to recruit 321 patients from 13 UK sites, and we've just closed follow-up this week, and we'll be hopefully presenting the results of that early in 2019. So that's fine if we accept that pulmonary vein isolation is as good as we're going to get it. But actually, we'd like to do better than 50 to 70% success rate. So what are our options? Well, one option is to go back to where we started, mapping atrial fibrillation and trying to understand what's driving the fibrillation. And we're particularly interested in the fact that Bordeaux had shown that there were these foci that were triggering atrial fibrillation from pulmonary veins. Now, of course, it's possible there are foci elsewhere in the atrium, and we just hadn't found a way of identifying it. So we went back to trying to understand and map atrial fibrillation. So Norman Qureshi is a consultant electrophysiologist now between High Wycombe and Imperial, and he started working on this project. And he used a catheter with 20 electrodes that he could move around the whole of the left atrium. And although this doesn't have as many electrodes as the array that I used to use, he was able to get and map the whole of the atrial chamber. And this is what atrial fibrillation looks like. So this is what these signals that we're trying to interpret look like. And one of the things that struck us was that within this so-called random activation, occasionally you'd see beats that looked very similar to each other. And it seemed a bit odd that this was purely chance. And maybe was the first signs that there may be something that we could map. So we'd been doing quite well with ripple mapping, so we were feeling quite bullish. And so Nick Linton, who was now a consultant electrophysiologist at Imperial and also a senior lecturer at the bioengineering department here, we went back to looking at these electrograms during atrial fibrillation and trying to apply some of the things that we'd learned whilst we were doing ripple mapping. And one of the things we realized was we couldn't use our bars, moving bars again, to do the same thing. But we applied some of the knowledge that we learned to do a different type of activation mapping, where we could identify the wavefronts on the chamber, on the catheter when it was being held against the wall of the chamber. So Ian Mann took on the mantle from Norman and started using this mapping process to look for potential mechanisms. So the first thing we were interested in was, can we find any of these sort of focal activation in other parts of the atrium? And actually he was able to do that. So here he's got the catheter up here, and you see 3 seconds apart there's this focal activation that takes place. The trouble was, we didn't know whether one of these focal activations would just happen to be there, or whether it was actually important from a mechanistic perspective. So we thought we actually had to properly map the rest of the atria to try and get an idea of this. So this is a 2-second period of atrial fibrillation, and Ian created activation maps of those 2 seconds of atrial fibrillation. You might recognize this because this looks not that dissimilar to what I was doing about 15 years earlier. The big difference was Ian could generate this in a matter of minutes, as opposed to my weeks that I had to do. But it also told us something else, that if this is what 2 seconds in one place looks like, multiply that by 15 to get a 30-second episode, multiply that by mapping the whole of the atria, 50 sites, how do you put that all together in your head? It was going to be impossible. So we realized that actually, again, we had to go back and think about how we interpret these maps. And what we sort of figured was that it was the direction of the wavefronts that was important, and how consistent they were across the catheter. So we created this idea of an orbital plot, which put together all the beats over a period of time. So here, most beats were going in this direction, and a few beats just slightly on the either side of it. And we could put that back onto the 3D map. And so we had a sort of a composite of activation patterns over a period of time that was being analysed and put back onto the atrium. And so Ian has just finished his PhD proving this idea works. And now we have to apply this to try and see what we can learn by using this type of mapping approach. So going back to this problem of other things that might be, what other things maybe we were missing? You should always keep an open mind. Could there be something completely different that we need to think about? And that completely other thing that we maybe need to think about is the autonomic nervous system. Now, I call that the forgotten frontier, not because among scientists, it's very well known that the autonomic nervous system is absolutely critical to driving atrial fibrillation and other rhythms. The autonomic nervous system controls the heart rate, it controls the heartbeat, so it's very important in the function of the heart. The problem is that interventional electrophysiologists like myself and the rest of our team weren't familiar in how to identify or manipulate the autonomic nervous system. So this was a real challenge. And Boon Lim was the man for the challenge. And he was tasked with something quite remarkable, which was, this was something none of us had ever done before. And we had no idea where to start. So he started by literally going through all the animal literature, trying to figure out what was possible to be done in patients. And what he came back with was a neurostimulator that he thought could be used in patients. And he set about trying to replicate some of the studies that have been done in animal models. So here, he's hooked up his neural stimulator to this catheter that is sitting in the left atrium. And there's this other catheter, which is sitting in one of the pulmonary veins. Now, when Boon stimulates this area, which he knows has got one of what we call a ganglionated plexi, or an area where there's neural nerve endings, he demonstrated that caused an ectopic beat within the pulmonary vein. So stimulation inside the heart, without any electrical conduction through the muscle, was causing ectopic beat within the vein. So this was one of the first demonstrations in patients of a neural connection between the body of the atrium and into the pulmonary veins. So this work was developed by Louisa Malcolm-Laws, who's one of our EP fellows now. And Louisa mapped those areas that we knew were sort of commonly had these gangulated plexi in. And she identified that in a particular patient, those areas were very specific and were very stable. And it was possible to ablate those areas and stop those ectopic beats happening. So although we were burning heart muscle tissue, it was the heart muscle tissue with nerve endings. And for this work that she did on characterizing these gangulated plexi sites, she won the British Heart Rhythm Society Young Investigator Award. But the question, of course, that's immediately apparent at the end of these experiments was, well, can we use these GP sites as an alternative for AF ablation instead of doing pulmonary vein isolation? So Belinda Sandler was tasked with the study trying to answer that question. So what Belinda did was she would move the catheter in the heart to identify areas that produce these ectopic beats. And she would map the whole of the left atrium to identify all the areas that did produce ectopic beats and the areas that didn't produce ectopic beats. And then just the areas that produced ectopic beats were ablated to prove that it was no longer there. And in a small feasibility study comparing GP ablation against pulmonary vein isolation, Belinda was able to show that the two treatments were very similar. So this in itself was quite remarkable because this was a completely different approach to AF ablation. But what was even more remarkable was that this was achieved with half the amount of ablation as for normal pulmonary vein isolation. So it was a far more targeted approach and was causing less injury in the heart. So obviously we found this result very impressive and wanted to develop it further. And of course, the first thing about developing anything further is you have to repeat it. So Maria Kim, who's one of our current research fellows, her PhD starts with trying to replicate Belinda's results with a different cohort of patients. But not only that, we were also interested to see whether we could teach other centres to do the same thing. So she worked with Barts Hospital, Plymouth and Leeds, training them in how to use a neurostimulator. And in that training process, and working with Professor Peters' electrocardiomats group, she produced one of the first maps of the autonomic nervous system in the left atrium. So the results of her study won't be available for another year or so. But we kind of thought, well, actually, let's assume that it shows the same. And if it did, how would we test it again at other centres? Now, the problem is these neural stimulators are quite difficult to use and difficult to train people in using them. So we had to try and figure out a way of making the procedure easier. So we consulted with Professor Drakakis from the bioengineering department, and him and his research fellow, Simos, started building a new stimulator for us. And Maria and the team tested this stimulator on isolated heart preparations from the Peters Fusion group, and have also worked with the Dyson School of Design to try and make the stimulator more user-friendly, and so something that could potentially be used in future to perform these autonomic therapeutic procedures. So that's where we've got to as a group in atrial fibrillation. So we're doing the AVATAR study as a way of saying, well, how well can we make pulmonary vein isolation work? We're using retromapping to try and understand the electrical activation of the atria. and autonomic modification as a potential alternative therapy for atrial fibrillation. Now, I'd like to move on and sort of finish off with another rhythm, ventricular fibrillation. And ventricular fibrillation is similar to atrial fibrillation in that there's a regular activation of the ventricles. The big difference is that with ventricular fibrillation, causes sudden cardiac death. And so the process of trying to understand and study ventricular fibrillation is far more difficult. And we were particularly interested in a group of patients who are young patients who have genetic abnormalities, who are prone to sudden cardiac death events. And so we were very excited when we were approached by a startup company that were producing a wearable technology, which was a 256 electrode vest, which when combined with a CT scan of the patient, they could use the electrical signal from the body surface with the anatomical information from the CT to actually produce activation patterns on the heart, as though we were doing an electrical study directly from within the patient. And this, remember, was done whilst the patient is awake and walking around. So it was giving us a huge amount of information that we were unable to do before. So Kevin Leong was the PhD fellow and now one of our clinical research fellows who set off on this task of trying to understand these maps. So like always, we always start looking at normal beats and what normal activation is. So here are the two ventricles during rest on a healthy person, and this is their activation pattern. We then made the patient run on a treadmill to peak exercise and then watch them recover. And you see here, the three maps are remarkably similar. So the electrical activation during exercise seemed to stay the same in these healthy patients. Now, what we were postulating was that patients who are prone to rhythm disturbances that cause ventricular fibrillation wouldn't display the same pattern of activation. So Amanda Varnova is one of our consultants who specializes in treating and screening patients with sudden cardiac death in their families or have suffered sudden cardiac death. And we were able to work with her to look at patients who had a condition called Brugada syndrome, which is a sodium channel problem, and VF. And you see in this patient, their baseline and their post-exercise is very different. And similarly, in a patient with what we call idiopathic VF, where we don't even know what the cause is, again, we see different activation patterns at peak exercise. So this was a potential for maybe risk stratification or helping us identify people that were at risk. So the problem was that, again, these isochronal activation maps take a long time to create. And it was very difficult for Kevin to be able to do this type of work in the sort of numbers that would be required to do any formal statistical analysis. So again, we turned to Professor Francis to help us try and solve this problem with Matt Shin, one of his fellows. And they were able to extract all the electrograms from the system and try and work out how best to do comparative algorithms between rest and exercise. We came up with this idea of the Ventricular Conduction Stability score, whereby in healthy patients, the activation pattern looks almost the same when you compare rest and peak exercise. So that looks white with a 100% score. And with patients with risk of sudden cardiac death, you see this abnormal patterns with the score dropping down to 89% because their ventricular conduction isn't stable under stress. So Kevin looked at different groups of patients, and whether it was idiopathic VF, Brugada syndrome, or hypertrophic cardiomyopathy, he found that the V-Cos scores in patients who'd had a sudden cardiac death event was lower than the patients who were control normals. And Kevin won the British Heart Rhythm Society Young Investigator Award for this work as well. So that sort of completes the current team. And now we look to the next generation. Jij here is taking on Kevin's work on ventricular conduction stability. He's clearly looking a bit anxious and thinks it's a long struggle ahead. George has taken over from Vishal to look at ventricular tachycardia mapping with ripple mapping, and he's about a month into his PhD and also looks rather anxious at the moment. Claire, on the other hand, hasn't yet started, but will do shortly, carrying on from Ian Mann, and she looks much happier, but we suspect things will change. So I'd like to finish with another royal birth and another end of an era. Because this time, this royal birth marked the end of the St Mary's cardiology department in the form it was. And we moved from St Mary's to the Hammersmith Hospital, where Charing Cross Hospital, Hammersmith Hospital and St Mary's have come together and formed a single cardiac unit with a research facility at the ICTEM building with the basic scientists, and soon, hopefully, to be joined by the engineers and a whole group of other Imperial academics, so that we can take forward the sort of things that we've been working on. So in terms of acknowledgements, obviously, I'd need to thank the entire EP consultant team, particularly Professor Peters and Wynne Davis, who've sort of mentored and supervised me over the years. But this team have really worked together, and we recruit patients together and solve these problems together. We're very grateful also to our funders, particularly the British Heart Foundation, who are our most important funder, but also to several families who've donated significant amounts of support to our research team, and to our industry collaborators who work with us on all these projects, both in terms of giving us manpower support as well as financial support. And then there are all the other NHS trusts and bioengineering department, the trials here, who are our collaborators, and our physiology team, who are very patient with all the research protocols that we do. So I'd just like to finish off by thanking the team.
Very nice move. Well, thank you very much. That was a tour de force, absolutely fantastic. Now, it's not the traditional to have questions. We don't have questions after these very special occasions, these inaugural lectures. So instead, we're going to ask the inimitable Professor Peters to come and give us his own special brand of a vote of thanks. So thanks. Thank you.
Thank you, Sean. Thank you. Congratulations. On behalf of the audience, I'd like to really congratulate you on an extraordinary, absolutely extraordinary lecture. I'm sure you'll agree. Science and practice. I mean, what more could you want? This is the ideal combination. If you look at any academic institution in the world and any source of funding in the world, this is exactly the combination that is the aspiration of everybody. And the Academic Health Science Centre, of which Imperial and Imperial College NHS Trust formed the first in this country, is based on the concept that the best research is done where the best patient clinical practice is performed, and the best patient clinical practice is performed where the best research is done. And Prapa's lecture absolutely epitomized and distilled that, and indeed Prapa personifies that. Translation from the laboratory into clinical practice, and from clinical practice into the laboratory was there for all to see. The multidisciplinarity, and these are words that appear in the strategies of every academic institution in the world, including this one. Translation, multidisciplinarity, working with the engineers, a very compelling offering from Imperial that has been harnessed by Prapa. And one thing that Prapa has taught me, amongst a multitude of things, is that everyone has their strengths. And so this combination of translational thinking, multidisciplinarity, and identifying all the wonderful smiling faces you've seen has been brought together to get the best out of everybody. And Prapa's ability to harness, identify and harness those strengths was epitomized here in general, but there's a few specific examples I'd like to refer to. So the historic continuum, I think, was relevant, and you know, Augustus Waller, who actually, if you like, sets the tone, and we are the legacy of Augustus Waller. I'm very proud, actually, to be electrophysiologists in Augustus Waller's wake. Just as Augustus worked with Jimmy, so Prapa identified Pippin, okay? And that was an inspiration. And that is one example of Prapa identifying Pippin's strengths, just like Augustus identified exactly the same strengths in Jimmy. And just in referring to those incredible smiling faces, I should say I did have a list of 3 examples. I crossed one out, but I'm going to refer to it. You'll notice the gender balance amongst those smiling faces, and I think it's very important. And I'd just like to illustrate the point that our funding bodies, our sources of funding now, take diversity and specifically gender balance to be so important that unless we achieve certain metrics of gender balance as an institution, we are no longer eligible for some of the sources of funding. So it has risen to the top as an extremely important matter, and it's one of the strengths that Pippin has, that Prapa has harnessed. Over the years, I've made that confusion so many times. So, for example, Maria Kim was identified as one of the smiling faces, and she's now teaching the rest of the world how to do her particular brand of mapping. And what a better strength to identify than that finger-wagging teaching approach that Maria epitomizes as a representative of her gender. And of course, another strength that Prapa has identified is the smiles. And this actually speaks to one of the strengths in the leadership that Prapa referred to, and the greatest strength of the leader of cardiology within our group, and that is Rodney Fole, whose greatest strength is his smile. Okay? And Rodney has set a tone that we've been able to continue, and that Prapa has been able to continue, of immense collegiality, and I think that came across in this talk. There is a collegiality at Imperial NHS Trust and Imperial College in the cardiovascular practice and research that for me is absolutely unique, and which we have defended, come all the changes that you've seen in the history of the recent history that Prapa illustrated. And despite all those changes, the core and the essence that it's been important to keep hold of, and that Prapa individually and all of us collectively have maintained, is that collegiality. And another great strength of Prapa that came across today is the way that his fellows have, amongst the other fellows produced by the cardiovascular clinical and research teams at Imperial, have populated a lot of the UK and indeed abroad. That collegiality therefore has spread, and I think all those individuals, many of whom are in this room, I think would acknowledge that it's one of the principal strengths and that Prapa has been able to perpetuate from our group. So, trust and collegiality and togetherness, together I think featured in your last slide when you referred to everybody. Multidisciplinarity, translation, these are all key words. These are what make an incredible research group, and Prapa's ability to do all of that is an absolutely extraordinary feat. And most of all, it's been fun. I think everyone in this room has identified how much fun it's been and how much fun it is to work with Prapa. So on behalf of everybody in this room, this entire audience, and the rest of the world if you're watching, I'd like to congratulate you on an incredible career thus far. Wish you all the best for the rest of your career, and to thank you in the usual way.